In last time when we met, we talked about direct delivery over a local area network, and then we start talking about indirect delivery and how it happened, and what is hop-by-hop network. This is an example just to show you when there is you try to print the sort of the routing information regarding that is stored to a host. You will find a number of different entries that shows you fundamentally either a destination as a network, a destination as a specific host, and so forth, and if the route is actually up, if it's a host, if it's a network, and there are some, you can find out if the destination is a gateway, so you know that you're going to send to that file in order to that host in order to reach the rest of the internet. If the route is to a specific host, if the route was created by a redirect message, we will see what it is, or if the route was modified by a redirect message. So the routing mechanism per se, it's very simple. You go through the list looking for something that matches the destination of the IP address, of the IP packet that you want to send. And when you find that destination, you act appropriately. Of course, if your destination is not listed, you will use a default thing, which is send it to the gateway. But if there is no way to find a destination host, you will generate a host unreachable message, and you will drop the packet fundamentally. So routing tables can be set statically, so you can actually have a configuration files that explain how to route the packets, or can be done dynamically using routing protocols such as RIP or other OSPF. There are various methods to actually route the protocol around. So let's look at IP spoofing in its basic form. We saw IP spoofing in a directed connected network. When you perform routing, since routing is fundamentally based only on destination, you can send your packet as spoofed exactly as you would in directly connected network. You just simply, create a packet that appears to come from a host that is not, associated with your IP address, and you send the packet, which will be routed and will reach the destination, and the destination will believe that the packet has been originated from this host. Of course, there are many things that are wrong with this picture. For example, there is no reason why, if I'm on this router, a packet from an internal network would come on this interface. And in fact, increasingly, internet service providers are blocking packets that are not supposed to be originating from a certain domain. So if you are, depending on the provider, you start generating spoofed packets with spoofed IP addresses that just drop. Say there is no way that this guy, for example, this provider, might say, I know that the 128.141 network is that way. There is no way that something like this would come in from this side. So it's called egress filtering, and prevents, for example, attacks like spoofing, denial of service attacks, and so forth. If it works, the idea of course, impersonating another IP address is to exploit some trust relationship that there is between the two hosts. So this host, believes this host for something. For example, is the guy who gives you information about, I don't know, domain names or things like that. And so being able to impersonate that host might affect the security of the services of this host. Of course, you can also perform man-in-the-middle attacks in an indirect communication. If you're a gateway, of course, you are in the middle in the communication, so you can do all the attacks that we saw in the case of direct connection through ARP spoofing. In this case, you don't even need to be, you don't have to do anything because you are actually sort of an intermediate step in the delivery. Another interesting point in the delivery of IP packets is fragmentation. So fragmentation happens when the datagram that you're trying to send is bigger than the link level maximum transfer unit size. So you want to send a big datagram, but you're sending over Ethernet, and Ethernet has only 1500 as the maximum size of the data, and so you have to actually break it down in small pieces. And this can also happen because you are on a on a point-to-point connection that has a weird MTU, and so maybe because they want to be more resilient, they make packets smaller, and so you have to break down your IP packet. This can be done at the source host, or can happen in intermediate step. So it could happen that you send a packet that is okay for Ethernet, but then later reaches a hop or a link in the delivery path that has a smaller MTU, and then it needs to be broken up. So we will see there is also the possibility of marking a datagram as do not fragment. So you can ask as a sender to not fragment your traffic. And in that case, if the packet reaches a link level transfer where the MTU is too small, the packet is just dropped, and then ICMP message is sent, and you are informed that there was a problem in the delivery. The IP datagrams are two flags fundamentally that are used for fragmentation. One is the don't fragment flag, and the other one is the more fragment flag. And these are used to actually break down the IP datagram. So once you have to fragment the datagram, you copy the header in every single fragment. What you do is, most important, put the same datagram ID, so you know that all these fragments are part of the same datagram, the same packet. And the more fragment is set except for the last one. So whenever you see a packet with the more fragment set, that means that there are more fragments to come, and the last one doesn't have it, and so you know it's the last to be processed. And once you received all the fragments, you put them all together and you pass them up in the sort of network stack. Okay, so there is this thing where you collect all these fragments, you put them together, you pass them up. So every fragment is a separate datagram. And so the fragment, of course, can arrive out of order, can be dropped by the delivery process. There are so many things that can go wrong, and therefore, actually, fragmentation, for many reasons, is considered something that you shouldn't do as much as you can. Okay? In certain cases, it's not, in certain network, it's not even permitted. As we will see, there are several problems. This is a TCP dump sort of trace of a fragmented packet, and you can see that this is the ID, and this tells you the original size, and this is the amount of traffic, and this is the offset at which the fragment should go. And this offset, sorry, I forgot to highlight it, but here is the fragment offset. This tells you in 8-byte chunks, because it's only 13 bits, so you can only specify offsets at 8 bytes steps. It tells you where this fragment actually goes. All right? So you can see here in the trace, you say, for example, oops. Here you can see that it tells you that this particular, 1,480 bytes of data needs to be put at this particular offset. A very famous case of use of ICMP and fragmentation to destroy the happiness of Windows users was the ping of death. This was just a little trick to use fragmentation to force the reconstruction of a packet that is bigger than 65,535 bytes. And you can see it here. Fundamentally, at the end, you can see that here, you're sending as the offset 398 bytes at this particular offset, which gives you this value. Once you had the 20 bytes of the header, you get 3 bytes more than 65,535. And since in the kernel, they allocated a static buffer for that packet, and here you can see a classic example of the assumption made by the developer. Say, well, a packet can never be bigger than 64K. So if I allocate a static buffer on the stack that is exactly that size, nothing can possibly go wrong. And here you can see how this little mechanism allows you to violate that assumption and cause a kernel panic, and therefore the blue screen of death. And so this was, you know, when I was in college or grad class, it was, you know, the way to boot people off their computers as a prank. It was the ping of death. Of course, you can do other things with fragmentation. First of all, fragmentation has always been used as a way to avoid detection. For example, oftentimes firewalls make decisions, you know, based on the one single packet. They don't reassemble the packet. And so you can do all sorts of tricks because you can send a packet, the firewall will look at it, will let it through, but then you can send fragments that can, for example, change the nature of the packets or delay certain contents that could be malicious or not. By the same token, there were several sniffers and intrusion detection system in the past that would not handle fragmentation. And so all these are different ways in which you can hide, in a way, your the nature of your traffic. Yes?
So if the network doesn't allow fragmentation, then you won't have packets bigger than 1,500 bytes.
Correct. 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 All right? So, and this is something that, unless you, of course, have, you know, two machines connected by something else that is not Ethernet, then you can have any kind of frame, you know, bigger frames and everything like that. So these are all, for example, you know, an important point is that if you have a TCP over IP, the first fragment of that contains only 8 bytes, so source and destination ports, but you can play with the syn flag, the synchronization flag, and therefore you can sort of play dirty trick. Another aspect of this that we will also see for TCP is that you can also play games with repeated fragments. What if I send to a machine first a fragment with content, and then I send afterwards, before the fragment is fully reassembled, the same offset but different content? Okay, which one will be used? Will generate an error? Will use the new data and override the old data? Will discard the new data because already has the old data? Depends on the operating system. Depends on, you know, what is the decision of the implementer. Also, of course, you can use, as I said, fragmentation to prevent IDSs from reassembling traffic and applying signatures in the other way. And most important, you can use fragmentation as a resource exhaustion attack. So as we will see also with TCP, whenever you have to maintain state, that's a security pattern that can be exploited. If I can force you to say, hey, I'm going to send you all the fragments but one. Now in memory, you are 64K of memory, except for one sliver of the last fragment, that you are holding, waiting for this last fragment to come. And you, of course, have a timeout, after which say, OK, got lost. You have to throw it away. But if I send you a lot of traffic, and you have to hold a lot of memory waiting for these missing fragments, suddenly you run out of memory. Suddenly you have a kernel panic, or you stop processing traffic. And therefore, every time, and we will see this in many cases in denial of service attacks, every time I have an imbalanced imbalanced relationship between the effort that I'm putting and the effort that you're putting in a transaction, in communication, there is the opportunity for a denial of service attack, okay? So, for example, imagine that you call a call center and you start a recording every time that say, what? Can't hear you, can't hear you. And so you start using every person in the call center to answer just a record. For you, the cost is nothing because there is no real person, you know, at the other side of the phone. For the call center, is a denial of service attack because they need to have a person dealing with this fake communication for at least some time, and you can take down the entire call center. Let's talk about the ICMP protocol. So ICMP is encapsulated into IP, so it should be actually classified as a level 4 protocol because it operates within an IP packet, but it's actually considered a level 3, a network level protocol, because its goal is to actually sort of regulate and handle non-ordinary condition in the IP delivery of messages, so errors and things like that. And ICMP messages can be requests, responses, or even very commonly error messages. The message format is very simple. There is a type, code, a checksum, and a bunch of data that depends on the IP messages. Example of these messages are, for example, timestamp. You know, you ask what is your idea of time to a remote host. Source quench, you can send ICMP messages to say, hey, you have to, we have traffic overload. Parameter problems where you can inform of erroneous content of IP packet. Most famously, echo request reply. This is the ping, the messages used by the ping tool. Time exceeded, also very useful. Whenever you have a multi-hop delivery, you have an interesting element in your packet, which is the time to leave. So the time to leave is a number that is decremented every time the IP packet is given to the next hop. So it starts, say, with 10. When I give it to the next hop, it becomes 9, and then 8, and so forth. This is to keep track of how long it took to deliver a certain packet. So that, for example, if there is a loop, what happens is that thing will go to 0 really fast because they're going to decrease continuously that number. And the moment it gets 0, the gateway drops the packet, puts the packet as the data of one of those time exceeded messages, and send it back to the originator. So when you don't see your traffic being delivered, you're like, oh, I'm getting time exceeded. That means that, you know, there is a loop in the network. Yes?
So what if the time exceeded packet gets stuck in the loop and then that packet gets dropped?
True. At that point, you're probably out of luck.
But I mean, would another packet get sent in response to your timeout packet being dropped? Could you create a packet store?
That is a very good question. So if a time exceeded packet gets in a loop, yeah, that probably they would attempt to send one of those back because they would be treated like any other IP packet. But to do that, you should be in a condition where sending from A to B through C contains a loop, and then C to A also contains a loop. So it might happen. At that point, nothing will work, fundamentally. Also, redirect, as we will see, you can use ICMP to sort of change the way people see routing dynamically. And also the classic destination unreachable, which tells you that, you know, this packet cannot reach its destination for a number of reasons. This is the ICMP echo request reply. There is, you know, the usual information. The type is either 0 or 8. There is an identifier, which is a process ID, and a sequence number. So this is how your classic ping looks. You're very familiar with this. You have your sequence number. They tell you where you are in this series of messages. You have a time to leave. So you see there. And you have the time between sending and receiving ICMP request and reply. Of course, ICMP are used for two main attacks. One is the classic ping sweep. So when you target a network, the first thing you want to know is the network actually, what are the hosts that are up in the network? And so what you do, typically a ping sweep, you send a ping message to every single address in your network. And you see who replies to you, and you find out which hosts are available. This is done very nicely by a tool called Nmap. Nmap is the tool for network scanning. Even for your research, for anything like that, you know, Nmap has an immense number of options to do all sorts of different scanning. And it's something that you can use for diagnosing problem, to understand what's going on in the network. It's an incredibly useful tool to have at your disposal. And also, you can use ICMP echo messages to do denial of service attacks. If you remember, there was that net-directed broadcast. So the basic idea is that you send a packet that is an ICMP packet, and when it gets to the specific network, it becomes, you know, a network-directed broadcast. So imagine that an attacker sends one of these packets to a bunch of networks, so sends a ping-directed broadcast. It gets to the network, gets broadcasted to everybody, and everybody will respond. So what if the source of that first net-directed broadcast is actually the machine that you're going to attack? So you send a message like, you know, this is the victim, 4110. This is the bad guy, say, hey, I'm 4110. Please, all you ping back to me. And of course, all these guys together are going to ping back to this guy. And if you use enough network, you will take down that particular machine. So this net-directed broadcast become an amplification attack. Again, these are classic pattern for denial of service attack, where you have the guy has to send one packet, and this network might send back 255. That's a 200-time amplification, which is, you know, 2 orders of magnitude is not too bad. Okay, you can do it even worse, trust me. But this is something that caused problems for a while, and that's why right now, if you send a net-directed broadcast, no router will accept your net-directed broadcast unless it's some router from the 90s that hasn't been updated since then, because it could be abused. But it's useful to understand, you know, these examples of very well-known attacks, because they have really a pattern that show how this can actually affect the network. Also, there is the ICMP redirect. This is an interesting thing. Fundamentally, is when you send, this is the sort of the good way to use the datagram. Suppose that a machine is connected to actually 2 gateways, okay? And it has to generate a gateway for a specific, it has to generate a packet for a specific destination. In this case, this guy is sending a datagram to WXYZ, this IP address, whatever that is. And since he doesn't have a destination, use the default gateway, which happens to be this one, okay? Now, this gateway know that the best way to reach anyone in the WXY network is to use a different gateway, the other one. So fundamentally, sends the datagram there, but also adds an ICMP redirect message to this guy saying, next time you want to talk to somebody on WXYZ, please use the other gateway. It's a much better way, okay? Once again, very nice. It's a way to optimize network delivery and to prevent this. So you have, you know, your nice packet that shows this is the router that should be used instead of me. So you can do redirect for entire networks or redirect for specific hosts. But normally only the one for host is used. So there are some checks. You cannot send an ICMP redirect and have anybody change their routing table as a consequence. The new router must be directly connected to you. So I cannot send something to say, hey, use as router some host somewhere in the internet. The redirect must come from the current router for that destination. So not anybody can tell you that. And the redirect cannot tell the host to use itself as a router, and the route being modified must be an indirect route. So it cannot be the route of a directly connected host, because it wouldn't make sense, because it's just use a different gateway. So if we're using a gateway, we're not talking to somebody who's directly connected to this. Of course, people found a way to redirect this, because, you see, look at this. Look at all the security condition. The new router must be on a directly connected network, fine, and the redirect must be from the current router for that destination. But there is no real authentication. This is IP. So you can spoof a message from the current router saying, hey, you should get somewhere else. And you can pretend to be a gateway by being directly connected to the host. So if you're a host, you're directly connected to the victim, and you know what is the gateway for that victim, you can spoof a message to the gateway and say, hey, send me the message. I will route them much better than the other guy. And of course, you can do this to do hijacking or denial of service attacks. So here, for example, you have an example. If you, on a Windows machine, because not all machines are vulnerable to these type of things, if you look at this, the route is like, pretty standard, okay? But if you see, you generate an ICMP message that redirect the 128.1.1.48.69 to host 100. Currently, if it would go anywhere else, okay, the default gateway would be 192.168.1.1. Here we're saying, if you're trying to reach this particular machine, then use this gateway instead, okay? And as a result, if you print that afterwards, you will see that there is a specific route here that says, hey, when you have to send to 69, now don't use the gateway, the standard, but use instead 100. And actually, when you start pinging that host, you will see that the actual Ethernet destination address is not the one of the gateway, but if you look, this is actually the one of 100, okay? So you have, in that way, impersonated the host. Then, of course, there is ICMP destination unreachable. There are many subtypes that say, hey, you cannot reach this particular host. The actual port is unreachable, or you need fragmentation, but you decided to mark that IP message as non-fragment, and so forth. And so you can use this in a number of ways. Of course, you can use that maliciously by spoofing specific forged destination unreachable messages that will cause the victim to shut down the communication. And so this, again, becomes denial of service attack. In this particular case, it's because you're taking an action that is security relevant, like shutting down a connection, based on information over whose source is completely unauthenticated. So here you are, another pattern of a security problem. Time exceeded is also interesting. As I explained, when TTL becomes 0, you send the packet. This is actually used by traceroute. Traceroute is a tool that is not an attack tool, but just tells you how a packet is delivered through the network. And the tool works by sending packets with increasing TTL. So they start with TTL 1. That means that you send it to a hop. The guy's like, oh, I just decrypted to 0. Send back a time exceeded. But since the reply contains the packet and comes from that gateway, I know that that gateway is the number 1 in the delivery path. Great. Now I put TTL 2 and I send another packet. It goes after the first one. The second one drops the TTL to 0. Send back a time exceeded ICMP packets. Suddenly I know what is the step number 2, and so on. And by sending continuously more packets, you can get a whole trace. This is an example. You start from my machine in my office. The first one is CS World 48, and then you see you start getting out of your CSB here. You enter the Caloran This is probably a pretty old trace, but you find out until you get to some place in San Francisco. So by doing this, you can actually see how your packet is transmitted through the network. And this can be useful in a number of cases if you want to understand how traffic is delivered within a network and so forth. Any question? Great. Okay, let's talk about the user datagram protocol, or UDP. You all know about it. Fundamentally, UDP doesn't give you much. It's a glorified IP packet that in addition has fundamentally a source and destination port and not much else. Okay? So it has all the properties of UDP. So it's an unreliable, connectionless, without guarantee of delivery, order, or duplication. So anything can happen. So everything that can happen to an IP packet can happen to a UDP piece of data. So the message is very simple, has fundamentally the source and destination port, a length, a checksum, some data, and is encapsulated. Of course, you will have an Ethernet frame, for example, or whatever is the link level protocol you're using. Inside you have an IP packet, and the UDP packet is the IP data. That's how you encapsulate protocol. And since IP is not much more than, UDP is not much more than IP, of course, UDP spoofing attacks are as easy. So you simply, for example, the attacker can send a spoofed UDP request. If there is a request reply protocol, the server will reply to the trusted client with some kind of value, but you can impersonate the trusted client with the server, or the server with the trusted client. So UDP-based protocols are, unless they use encryption, they're especially prone to all these different type of attack. For example, DNS is typically very vulnerable to DNS hijacking because, of course, you can impersonate the DNS and confuse the attacker. You can also, since you have a request or reply, you can also hijack an interaction. So you can sniff the network and wait for a UDP request and then race for a UDP reply. For example, many security tools, when they have, for example, to prevent somebody to connect, and they cannot really be a man in the middle that blocks the connection, they use as a technique the injection of annex domain DNS packets. So you try to resolve something. I don't want you to connect to that. I just send you something from the DNS, say, that domain doesn't exist. It's like, what do you mean that doesn't exist? I say Google doesn't exist. And since they can convince you, you stop being able to connect. So it's a useful technique to prevent connection. Another way UDP can be used is to do a port scan, because UDP introduces the concept of port, and so you want to know which UDP ports are actually open on a specific host. What you do fundamentally, you send zero-length UDP packets to every single port, and if you get an ICMP error, say port unreachable, that means that the service is not available. If otherwise the system is silent, okay, then you will assume that the port is open. Assume, because there is another aspect to it, that because of various denial of service attacks in the past that involved ICMP, most operating systems now limit the number of error messages that are generated in a certain amount of time to prevent people to become sort of reflectors or amplifiers for denial of service attack. And so the main result is this port scan can be quite slow. Of course, this is supported by Nmap. So you just, you do Nmap SU, and you will see, something that tells you, this classic Windows machine has some NetBIOS ports open. Yes?
Why does the packet have to be 0 bytes on the previous slide?
That's a very good question. I think it is mostly because that a zero-length packet will be ignored by any protocols. because it will be, oh, you send me something for my protocol, it's empty, I'm not going to do anything about it. Will not generate errors. So it has a reliable known answer for all ports. Okay. Here you have, for example, a trace. You can see these are the UDP packets. They are sent with 0. And you can see that little by little you start receiving these port unreachable messages. But you can see that 37 and 38 are not listed here because they're actually open. So the silent ones are the actually open. UDP can be used also, of course, for all sorts of denial of service attack because there is no concept of session that you can say, hey, I have no session open, I drop this packet. Every packet in UDP has its own full life and needs to be processed. And so this is makes you vulnerable to having to process all packets. You cannot easily discriminate. In some cases you can, in some cases you can't. But it's not surprising that there is an attack called Fraggle that does exactly what Smurf used to do. They used to do UDP packets, exploit the net-directed broadcast to expand and get a ton of reply that would hit a particular victim. Because of both Smurf and Fraggle, net-directed broadcast is, never implemented. And, we're going to take, let's go on for another few minutes. Let's talk about TCP. So we're done with all our transmission protocol. Yes?
How can you know if the port is open or it's just a packet loss?
You don't.
Okay.
This is a very noisy, very non-reliable scan. TCP is the Cadillac of transport protocol. UDP didn't give you anything but ports. TCP gives you everything. Look, it's connection-oriented, it's reliable, there is no loss, no duplication, no transmission error, correct ordering of the data. Wow, that's the thing that we wanted. So the cool thing is that fundamentally TCP creates a virtual circuit between two machines, a source IP address, destination IP address, source port, destination port, and this connection is duplex, full duplex. It means that data can go both ways. If you think about it, the rule is on the internet at one time, there are no virtual circuits with the same qualifiers. So two hosts cannot have two virtual circuits on the same source and destination port. Okay? Those 4 numbers at any moment in time for all connections on the internet are different. Is that clear? That's a classic test question. So remember it. Just kidding. But this is also called the socket, and the two streams are called socket pair. The TCP header is a lot more interesting than the UDP header. You have your source and destination port. You have these 2 numbers, sequence and acknowledgement, that we will talk about quite a bit. We have a bunch of flags, and then you have the header length that allows you to determine if there are options. There is a window, as we will see, allows you to check if a certain fragment should be, a certain frame should be accepted or not, and other interesting stuff. Like in the case of UDP, if you have an Ethernet frame, you put inside an IP packet, and you put the TCP packet inside the IP data. Let's talk about those sequence and acknowledgement numbers. So the sequence number tells you within the stream where is the data that you're sending. So I always fail to give him back the thing, so I still owe you this back. I promise I will give you 2 back. 2 back will come soon. So if this is the stream, fundamentally your sequence number is saying, hey, I'm giving you, if this sequence number is 27, this chunk of data in my TCP packet is from byte 27 on. Okay, so put it here in the stream. So this allows the receiver to put together the same thing. Okay. Then the acknowledgement number is sent back saying, hey, if the acknowledgement number is 73, on the other side of the connection, you can say, by the way, I received everything up to byte 73. So this is a way to tell the other guy, hey, I received your stuff up to 73. So if you keep sending, but my acknowledgement number is not increasing, that means that I didn't receive the data and you have to resend it. Because otherwise my acknowledgement number say, I got it, I got it, I got it, I got it. That would work. But in this case, it wouldn't work because the packet has been dropped, and therefore I cannot acknowledge because I haven't received the right packets. And sometimes maybe I received packets afterwards. I received this, so I received all this, and I received this, but there is this gap here, and so I cannot advance my acknowledgement. I can only, because if I would advance to here, I would tell the other guy that I also received this packet, which instead I haven't. And so a non-increasing acknowledgement number means, hey, resend your stuff. I'm still waiting for packets from 74 on, okay? So an acknowledgement means I have received up to this number, and the next byte that I expect is my acknowledgement number, okay? So these are important numbers that are used to make sure that the reassemble of the connection happens in the right way. And then you have the TCP windows, which fundamentally tells you, you see these packets that I haven't received yet. If they are within my window, then I will happily accept them. So I will, consider them, and I will make sure that I keep them in my reassembly queue. And therefore, I only accept a sequence number that is between the ACK number and the ACK number plus the window. You can modify the window size to affect the communication. The bigger is the window side, the more stuff you will accept from the guy, before you, for example, decide, hey, I'm missing some pieces, all right? And so you will have to use more memory, for example. If you have a smaller window size, you immediately you start not accepting certain packets if the guy is sending too much data to you. You will say, hey, I'm reducing my window, and therefore I will make sure that you only send me the stuff that I'm really waiting for at this point, okay? And we will talk more about TCP after a 10-minute break. See you in 10 minutes. So the most interesting part of TCP are those flags that you saw. The SYN flag marks the request of synchronization of the SYN and ACK number, and specifically represent the first packet in a connection request. The ACK flag states that the acknowledgement number is actually valid within the packet. And as we will see, all packets except the first have the ACK flag set. FIN is to mark a packet that requests the shutdown of one direction of the connection, and it's called a graceful connection. Reset is sort of like an abrupt request for shutting down. That means I reset, I don't want to ever talk to you, go away. It's almost like a breakup. Urge states that the urgent pointer is valid. So if you remember, in the header of a TCP packet, there is an urgent pointer. The urgent pointer is a very rarely used and very not understood concept of TCP. The basic idea behind it is that you could use it to send to a receiving application something that says, hey, by the way, you received all this data. The data pointed by this pointer is actually more important than other, and so it should pass to a higher level application and bypass the normal order of processing. This is fundamentally never used, but that's what the urgent flag is. And then there is push, which is a sort of a way to tell, hey, this is some data, immediately send it up to the receiving application. Because of course there are two levels, right? There is the level in which the kernel puts together the data as it receives the packets, and then there is the level where this data is made available to the application level program that will do a read from a socket, and then the data will be returned. This is a flag that says, hey, push it as soon as possible to the application that is reading this data. Don't buffer it in the kernel for a long time. So how do you set up a virtual circuit? The server is listening on a port. Yes?
Is the push actually being respected?
Yes. Yes. There was a question, though, about the four numbers.
Yeah.
But you're eating. You want to ask it later.
Yeah.
Perfect.
Sorry.
No, that's perfectly fine. So how do we establish a TCP connection? You start with a packet with a SYN flag set from the client to the server. The server is listening to a specific port. As you will know, this is done using a bind and a listen system call that says, hey, if somebody sends a SYN packet to this port, make it talk to me. And the initial packet contains a random initial sequence number called SC. Then the server answers with a segment with the ACK flag and the SYN flag set, okay, because this is a synchronization of the acknowledgement and the sequence number. And also the server as an initial random number, let's see, sequence of the server, plus returns in the acknowledgement number the sequence number plus 1, okay? And finally, at this point, the two numbers are synchronized, and the client sends a final segment with just the ACK flag set that has the sequence number increased by 1 and the acknowledgement number, which is the sequence number increased by 1. Okay? Now, we will see why we choose a random number. Do you guys have an idea why? Excuse me, maybe you missed some in the class. We don't allow laptops or phones. Thank you. You see my new face, so I don't know if you are new at the class and you were in the presentation. I'll give you the benefit of the doubt. Thank you. So at this point, what happens is the numbers are correct. Anybody has a guess why it would reply with the sequence number by the acknowledgement number increased by 1? Yes?
So that the other guy knows that it's actually the correct, that they actually managed to send up.
But I could have sent just SC, right? Y plus 1.
So to indicate that you're ready to receive the next chunk of data?
Not really, because the sequence number could be, I'm ready to receive, these are random numbers, so it could be anything. Yes?
3 transmissions, and the same packet comes through, and you get an acknowledgement with the same sequence number, and the original packet with the same sequence number. Would be the conflict.
No, that would not happen. Yes?
What about a packet left over from another connection that's floating around and could be
This is random, and so that would not happen.
Just send the packet. I mean, I received until packet 75, now 76.
Yeah, but this is the initial sequence number. So why in the establishment I have to increase by 1? Yes?
Where in general, if you have 2 connections, do you need to know which one you're responding to?
No, you always have 1 connection because the 4 parameters, source, destination, IP, and port are the same. This was actually introduced to make sure that you understand the correct endianness. So by returning something plus 1, you're proving to me that you understand how to take a 4-byte number and increase it by 1. If you have the wrong endianness, increasing by 1 would make it an enormously bigger number. And so by increasing by 1, if you just repeat to me the same data, I don't really know if you understood the data. But if you prove to me that you increased by 1, you say, oh yeah, I got your number. I can increase it by 1. I am operational now. And to you can seem obvious, but at the beginning of the internet, this was not that obvious, okay? Of course, right now, thinking that somebody doesn't understand this while running a protocol stack would be crazy. But you have to understand that this is, 1983. Okay, so if you look at the TCP standard from the beginning, they said, how do you choose the sequence number? Say, just have a counter and increment it every 4 microseconds. So linearly increment your sequence number every 4 microseconds so that you prevent reuse and confusion in a number of ways. BSD Unix system initially used something that incremented by 64,000 every half second, and then another 64,000 every time the connection was established. So it was a monotonously increasing number that would have bumps, at specific connection establishment, right? So this is how a three-way handshake, the classic three-way handshake happens. This goes to from port, usually a high port to, in this case, secure shell. There's initial sequence number, 0 acknowledgement, SYN flag sat, no other flag, and then the reply as both the SYN and ACK, okay? And I choose a different sequence number and contains as acknowledgement the sequence number increased by 1, and the final ACK has the sequence number following the initial sequence number plus the acknowledgement of the sequence number increased by 1. That's how it looks graphically, and this is your, classic TCP dump trace. You can see that there's a SYN, ACK, and an ACK. This number are very big. They're 4-byte integers, so they can vary quite a bit. Note that you can also, there is an option in TCP dump to see only the relative sequence number, so you will see only the sequence number from the initial establishment on. So if you get, fundamentally, this number would be 1 in that setup. Okay, data exchange, super easy. You send a packet with a sequence number, with a sequence number and some data. The other guy sends back a packet that acknowledges how much has been received. You can send an empty packet with just acknowledgements to say, hey, I received this data, but I don't have to send you anything. So this is an example. You send 25 bytes. This guy will send an acknowledgement that has the sequence number plus the 25. So I acknowledge that I received everything correctly up to this number. And this could say, OK, I got you. And you can see that in this case, the acknowledgement, that's an error because, oh no, there's 30 bytes, yeah. The acknowledgement number is completely empty, has no data, but acknowledges the 30 bytes sent by the server to the client and restates that, we are at sequence number 6,600. That means that the communication is now synchronized state. That means that both client and sender agree on their sequence and acknowledgement number. And this is how it looks in TCP dump. You can see this is some push flag. You can see that these are 3 bytes of data. This is the sequence number. It's telling you that this is the data from 66 to 69, 3 bytes, and acknowledges whatever has been sent before. So before it was sent from 62 to 77. So this acknowledges whatever has been received, sent 3 bytes, and finally the acknowledgement that these 3 bytes have been correctly received. Okay? Great. Shutdown. There are 2 ways to shut down, as you will see. The FIN shutdown means that with a FIN packet, you shut half of the connection. People sometimes don't understand that. But if I send a FIN packet, say, I'm done. I'm still listening to you. You can still send me back anything you want. But from now on, I will only acknowledge your data. I will never send you additional data. My half of the communication is done. The other person can send back data until they decide to send you a FIN message. At this point, you acknowledge that message, and then the connection is really shut down. Okay? So this is how it works. You have something marked with ACK and FIN, means I'm not going to send you anything. You can see the server keeps sending data back until it decides, oh, I'm really done. And then there is the final acknowledgement of this packet, and at this point, the communication is completely shut down. Yes?
What would happen if you opened a bunch of virtual circuits and you managed to cause all those last packets to drop so that the final act never got transmitted?
Well, after a while, the communication will just time out. Okay, so there are a number of timeouts in the kernel that decide, how a communication is handled. For example, you might be familiar with the concept of keep alive. There are certain, you can configure connection to send, packets, empty acknowledgement to just keep the connection going. But in general, as you will see, you maintain a certain amount of state, and therefore at a certain point you have to make a decision about what state about a TCP connection you're keeping and what you're throwing away. This is more relevant in the half-open connection, as you will see in a second. But it's a good question. So this is how a shutdown looks. The fin on one direction, the acknowledgement, the fin in the other direction. That's how TCP dump marks fin packets, and the acknowledgement. Of course, we have TCP port scan, and we have also UDP port scan, and we have TCP port scans. So this is just a way to find out what, is it a question? No. Only to find out which ports are open on a certain machine. The most obvious way to do it is called the connect scanning, which meaning you do full open a TCP connection to every single port. So you do, 64K, so 65,535 connection, SYNAX in. If you try to connect to a port that is closed, you get back a reset. Say, don't talk to me. That's what reset is done. The advantage of this type of connection is that you don't need to be root. Anybody on a machine can run this. Of course, it's very noisy because it will create a ton of logs, because most operating systems create logs for every successfully open connection. So people get smart and did things differently. This is how Nmap with -st does a connect scan, and this shows a server with a lot of services running. A stealthier way to do connections is using a SYN scan. A SYN scan requires root privilege, but it's much better because you send one SYN packet, and then you look for a SYNAC reply to tell you that the port is open, or a reset, and you don't do anything. You move on. In this way, you know which ports are open, but you haven't established a full TCP connection, so no logs are created by the operating system. So this, is a way to sort of hide your, actions in the network if you want. Okay, and of course you can always send a reset so that the connection is not even closed, and the connection is not open, not timed out, and generates no error message. This is how a SYN fag looks. You can see the SYN packet being sent, and you can see that the replies are sent for ports that are closed. Okay. Another way to be stealth is to use the fin scanning. In this case, you start sending a fin packet to a port. You don't have a TCP connection. So what happens? If the port is closed, the port sends back a reset. And if it's open, the fin packet is ignored. Okay? So this is another way. You have two different behaviors for the same action, depending if it's open or closed. You can scan the ports remotely using this attack. There is also a variation of this type of attack called the Christmas attack, because you set up all the flags, and so it's like a Christmas tree because everything is light up. Or the null, where no flags is set, and once again, you create some error condition, fundamentally some packet that shouldn't exist, and the operating system will reply in two different ways, with an error message or with doing nothing, depending on the fact that the port is open or closed. Okay? And you will find all sorts of tools that look for this type of attacks. But here you can see your fin packet. You send a bunch of things, and you can see the reset for all the ports that are actually not port 80. Okay? But port 80 is silent. There is no reply back because the FIM packet has been sent. Port 80 is open, as shown here, and there is no reply sent back. Okay? Want to ask you a question?
Yeah, like when you mentioned something like 4 different numbers to be different.
Yes. So I was talking about the TCP virtual circuit. So we have been talking about this the whole time. So there are 2 hosts, right? And you have an IP address. Actually, I think I can use one of these pictures before. This guy. So no, that's not a good picture. You have 2 address. You have X, Y, W, Z, and ABCD. These are 2 IP addresses. And you have a source port, say 11,203, and you have a destination port, say 22. These 4 numbers, 1, 2, 3, and 4, identify this TCP virtual circuit. And on the internet, you can have this host from this port connecting to port 22 on X, Y, W, F. Okay? There could be another circuit that is happening this way. No problem. You can share the source port. You can have the same destination port, but these 2 numbers cannot be the same. This virtual circuit will be defined by this, 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 and this, and therefore they're different. So these are the 4 numbers. Is that clear? Great. Okay. There is another interesting thing. It's called the idle scanning attack. This is a very cool scanning that the basic idea is to make the scan appears to be originated from a different host. So you want to find out what a port scan is, but oftentimes port scans are perceived as an attack, as malicious activity, especially when you're employing stealthiness and you're doing a thin scan. Say, why are you trying to avoid detection? If you're, and this once again becomes an important ethical question. Why you're doing the scan. In our research as security researchers, we scan the internet all the time to find out, how many hosts are, have this port open. That's a perfectly legitimate, question, and scanning for that is not an ethical action. You're just studying the internet, and you're a scientist, so that's what you do. But of course, for example, we set up when we originated our scan from a specific machine. We set up on that machine a nice website that say, hey, if you think that you have been scanned, we are researchers at UCSB, we're doing this project, we're not trying to harm you. And if you want to be excluded for the rest of this lab life from any scan of the internet, just let us know and we take them off. Okay? So it's true that scanning is not necessarily a malicious activity, but you have to be careful. People become sensitive when they're scanned. It's sort of like if somebody is looking into your house, a binocular, you were like, why are you trying to do that? And it's like, oh, I want to make sure that you don't have, this very dangerous plant in your garden. It's like, yeah, sure. It has to be done the right way. This is a way to actually exploit sort of a very intricate relationship between 3 different hosts so that it appears that the scanning attack comes from another person. So the basic idea is that you fundamentally send a spoofed TCP SYN packet to the host that you want to scan, setting the IP address, source IP address, to your relay. Okay? The relay will be the host that appears to be sending this thing. Now, depending on the fact that the port is open or not, you will send back a CNAC or a reset. But you remember, in blind IP spoofing, you can send a spoof IP packet, but the reply is not sent back to you. it's sent back to the relay. So how do you know, if one packet or the other has been sent? Well, if the target send a CNAC packet, so the port is actually open, then the relay will send out a reset. If the target replies with a reset, the port is closed, the relay will not send out any packet. So what do you do? Well, you probe the IP sequence number of the relay to see if it has increased by 1. This is a moment of glass eye, but I have the figure. Everything is going to be solved by the figure. So you can see that at the very beginning, the attacker interacts with relay only to find out what is the ID 1234 used by this to mark their IP packets. Remember the IP packets have an ID? That ID increases monotonically in many implementation. So it goes 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, sorry, 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6, and so on. So the next step, this establishes the fact that this guy's ID is 1, 2, 3, 4, thanks to the reset that is sent back. No information is gathered because it's really the victim that wants to be scanned. So this guy is going to send a spoofed SYN packet that appears to come from this guy because it's spoofed, and he say, is your port 80 open? This guy will say, okay, yeah, CNAC, and we'll send it this to the relay. But the relay say, what? CNAC what? I didn't even ask you if your port was open. Reset, go away. But sending this reset, your ID is 1235. Next step, the bad guy is going to check once again. What is your IP? And say 1236. Now I know that this guy sent a packet out. What happens when the port is not closed? So if the port is not closed, this will send a reset. And this guy was like, reset what? I haven't asked you anything. Reset you. They're not going to say, it's not going to say anything. Ignore it. So when in the next step you check, the ID is still going to be 1235. So now I have performed a scan, made it appear as another guy, okay, and I know which ports are open. Yes?
But that's assuming the relay victim is not talking to anyone.
Exactly. Very good point. So in order to do this, you have to choose the quietest possible host. And, find an unused host that doesn't do anything. And also, you can run this many times, and then, you will have some noise that you have to filter out at a certain point to say, well, most of the time, that's what happens. But absolutely, I wouldn't do this if you're, this guy is downloading a huge movie, his IDs are going to go crazy. You cannot really do it effectively. Yes? Also, if the sequence numbers are random, can't do that. So you have to find somebody who has an IP stack that generates sequential packet IDs and is very quiet. Okay? Good luck. So another interesting thing that you should be aware of is OS fingerprinting. So one thing that is interesting, TCP has so many parameters, ICMP, UDP, IP, all these different, slightly different way in which different operating systems reply to different phases of all these protocols allow you oftentimes to tell you what is the operating system remotely without having to log in into a machine. This is called OS fingerprinting. This can be done actively, where you actually send packets and try to fundamentally traverse a decision tree to get to the point where like, oh, okay, now I know it's exactly this operating system. Or you can do passive OS fingerprinting, where you're just listening to the connections and you're able, for example, to determine if a certain machine has a certain characteristic. It's Linux versus Windows versus Mac OS and so forth. Okay? And the things that you can look at is, you can undefined flag in the TCP header. You can send these flags and get back something if they are copied exactly. Where combinations of flag how the initial TCP sequence number are selected, window size, ICMP message, error rate, all this stuff can be put together in active OS fingerprinting. Passive OS fingerprinting, of course, is a lot more difficult because you don't have the way to probe. Of course, guess which is one of the best tools to do this is Nmap, but there are also tools like POF, that is really passive fingerprinting, and EtherCap that are able to do it for you. So remember, Nmap is your friend. They have a ton of different specification, and they can be incredibly effective in active fingerprinting a remote host. Of course, you're also the countermeasure. You can actually modify your kernel to drive these tools crazy by sending all kind of weird replies, but that's a different story. TCP spoofing, we talked about how to do IP spoofing. TCP spoofing is a lot harder, as you will see, because in this case, in TCP spoofing, you have to establish a connection with a remote host, okay, with a spoofed IP address, okay, and we will see why that's hard. And that's the type of attack that was used by Kevin Mitnick in the San Diego Supercomputer Center, which made it one of the first appearance in the wild of this attack that until then was considered just theoretical. So how does it work? So fundamentally, you have to have a node, A, that trusts another node. That means that if your TCP connection comes from that IP address, you're going to do something important. For example, you're going to let log in. The classic example could be, remote shell. The old protocol remote shell had this configuration that if your TCP connection was coming from a trusted host, you will take that command and execute it. Bam, like that. Yes, exactly. But this was because, like, with UDP it would be crazy, right? UDP, you send a message, it's done. But with TCP, the idea was like that it's very difficult to spoof a TCP connection. And so in order to do spoofing, you actually have, first of all, to prevent the spoofed impersonated host to do anything. So you do a denial of service attack, ping of death, whatever is your equivalent to take it off the network. Okay, so it will not send a reset. And then C sends, the attacker sends a TCP SYN flag to the victim A, impersonating B. Okay. The victim A will reply to B with a CNAC, but it will be ignored because you killed B and it's out of the network. And then finally, C replies with a CNAC, C will not receive this message and send the last part of the three-way handshake with possibly some data. Okay? The problem that you don't know what sequence number has been chosen by the impersonating the victim in your reply. And so either you sniff the packet, so you see the message, in that case it's easy, or you have to guess it. Okay? And here is the idea. Step 0, denial of service attack. You kill this guy. Suppose that any connection coming from this guy to this guy is privileged. That means that if this guy asks this guy execute a command, this guy will say, oh, you come from this IP address, you're a TCP connection, I'll do it. What happened in the attack is the first packet say, hey, execute this. This is going to say SYN-ACK, sending the initial sequence number, 54,002, to this guy. This guy will ignore this packet. And now, automatically, the third step, it has to send an acknowledgement which has the sequence number increased by 1. If you don't have this, no chance. This you know because you chose it, okay? But you have to guess this. And so the basic idea here is that what in the Kevin Mitnick attack, what happened is that they would open a ton of connections to this host directly and observe how the sequence number was chosen. And then they would predict the next sequence number. This is because it wasn't random. it was actually increasing monotonically. And so even if it was increasing very fast, you could always try to guess it. You could sort of like imagine you open directly, not non-spoofed connections, because you can talk to this guy. And so you can see how you're choosing connections. So imagine doing something like this, where, you know, you guys are scientists in time, you would say, oh, look, this guy is choosing this thing like this, probably not a good curve, but something like this. And then you can say, look, now on my spoofed attack, I'm going to try to use this value. And you might fail a few times, but eventually you will be able to predict the right sequence number. You will hit exactly the right acknowledgement number, and you're going to be good. You're going to execute commands or do whatever you want. Okay? So the because of these attacks, people say you have to randomize your sequence number generation. And a few years ago, Michael Zalewski put together a paper called Strange Attractors and TCP/IP Sequence Number Analysis, and updated it a year later. And he did an interesting thing. He just looked at different operating systems and created maps in which the values would be based on various difference between sequence number as generated in a sequence. Okay? So if you look at this, these values are based on the difference between 2 and 3 sequence numbers ago, 1 and 2 sequence numbers ago, the current and the current minus 1. So unfortunately, usually this is not very visible, but you can see that here there is some kind of pattern. If there is a pattern, and the pattern is very dense, that means that this can easily predict it, because that means that the differentiation between sequence number in a sequence are not sparse, but they're very close to each other. This was Windows 2000. This was Windows 95. And you can see that the choice of this sequence number is not exactly very good, because they have all this conglomerate, and that means that this is easily predictable. Linux is very random, so it looks like a cloud of noise. FreeBSD, even more random. You know, this is what you want to see, something that is completely random. This was Cisco iOS before the cure. It came out, say, hey, look at these patterns. You guys, you know, are not doing a good job. And after the cure, you can see, probably you can barely see, but it's really random. They got it, no? Mac OS X, also very random. This was HP UX before the cure. Then they make them notice that this was obviously some problem. After the cure, it still wasn't as sparse like the other. So it was interesting. There was an IRIX thing. You cannot see, but there are like fundamentally 5 points here. So, you know, it's completely predictable. And this is a very old paper from a long time ago, but it shows you, I mean, it's not from the 80s. This is like, you know, a few years ago, and it shows how certain stack implementation, network TCP/IP implementation still would not get this right. We talked about spoofing. We have now to talk about hijacking. So if you remember, hijacking means that you have an established connection and you insert something. For example, suppose that you have some initial authentication that you cannot, you know, observe, but then you have an established connection. You want to insert some data, and you can do it. Of course, you have to have the right sequence and acknowledgement number, and that's a difficult thing. So either you eavesdrop the traffic, or of course you have to guess it. Guessing now requires 2 levels of guessing. You have to guess the initial sequence number, and you have to guess how much data they have exchanged so that you get the right number. There is a paper that describes this attack. And the cool thing is, this is something that can actually end up being like a man-in-the-middle attack, because there is because of the injection, you have a sequence desynchronization. So you wait until both the client and the server has the same, they agreed on their sequence and acknowledgement number, so no data is being exchanged. And then you inject a spoofed segment that appears to come from one of the peers and has the right sequence and acknowledgement numbers. The other one will say, acknowledged, I got yours, because there is no authentication on TCP/IP apart from those two numbers. If you have those two numbers, you can inject traffic in the connection. But the acknowledgement will be received by the actual guy who hasn't sent anything. And like, no, these numbers don't make sense. I didn't send you 5 bytes. Acknowledgement, -5. The guy said, no, I received your bytes. Acknowledgement. And they start acknowledging each other. They call an ACK storm. Because you will see an enormous amount of traffic of these guys sending ACK to each other. Saying, no, you're wrong, 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 you're wrong. Until one of the two thing will drop, the packet will be dropped for some reason because they fill the connection, the medium. And then since empty acknowledgement are not acknowledged, suddenly everybody's like, okay. And they will quiet down until they try to communicate again. It was like, acknowledge, and they will not be able to communicate anymore because any attempt at communication will generate this ACK storm that will prevent them from agreeing on the data. So, but the data that has been injected, right? And now you can inject it in the other direction and desynchronize that because you have the right number. And at this point, you have full man-in-the-middle attack because this guy is going to try to send something. You can take it out. This will cause an ACK storm. You can resend it with the right sequence number that you now know. And the guy say, oh, finally you got the right sequence number. Acknowledge. No, I didn't do that. And they're going to start another ACK storm and so forth. But fundamentally, you have now full control over the communication. So this is the basic idea. You just observe. You have in a quiet state, you have the client sequence number that is equal to the server acknowledgement number and vice versa. And so you send the spoofed TCP packet saying, hey, these are 30 bytes of data. This will say, hey, now my new acknowledgement number is your sequence number plus 30. And this guy say, absolutely not. My sequence number is this. And then we'll go on and on and on. So yeah, this is how it would look like. You see, you can see the push of a packet, and you can see that after that, they're like, ACK, 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 and they're just fighting against each other, saying, hey, your ACK is, 112, and they say, no, it's 133, no, it's 112, no, it's 133, and they will go on and on and on. Another interesting attack based on TCP is the SYN floating attack, also known as Neptune. And this is a denial of service attack, very powerful, because the basic idea here is that you send one SYN packet, you receive the SYN ACK, then you don't do anything. Now there is a nice data structure in the kernel that keep track, oh, I receive a SYN, I send a SYN ACK, I'm waiting for the final ACK. And you will keep that piece of data there until the final acknowledgement, and then you will, it will become an active connection. But your initial SYN can be completely spoofed. Okay, you don't need to send it from yourself. You can just, use a bunch of spoofed address. You can have a botnet with a few 100,000 computers, each, hitting a particular port on a particular host. After a while, first of all, you will have to keep all this information. You will fill the queue of half-open connection, and you say, I'm not accepting connections anymore. Suddenly, the guy is down. Yes?
Is there any kind of authenticated TCP or any way you can verify that the IP address does actually belong to someone?
No, there is not. You cannot verify that. I mean, you can use IPsec. IP version 6 provides way to actually do authentication, but IPv4 does not. An IP packet is an IP packet, comes from this IP address, it's a SYN connection. You have to make a decision based on that information. And this is a pretty pretty effective attack. Current solutions are fundamentally filtering. You can increase the length of your half-open TCP connections. You can, make them time out faster, or you can drop connections. If you reach the limit, you start dropping the old connection, and you get more half-open connections. But at that point, you incur the risk if you have a slow opening connection that is legitimate to drop that connection, or you can use SYN cookies. Okay, and I think this one interesting use of SYN numbers. So this is actually a very kind of interesting security measure, because they really had to find a way to do this so that they did not have to keep state. So the basic idea is that you receive a SYN packet, okay, requesting a connection. You send back your SYN value that is actually a special value encoded in a certain way, and then you forget about it. You don't keep any record of it. If they are good guys, they will come back to you acknowledging that sequence number that you sent them. And only then, when you have the third step of the handshake and you know that this is not a SYN attack, it's not a SYN folding attack, then you will verify the number. If the number checks out, then it's great. So how do you choose the sequence number? Well, you use a timer that increases every few seconds, 64 seconds. Then you use 3 bits to encode the maximum segment size. That's something that you need in establishing the connection. It's one of the parameters. But the most important part is this, is a keyed hash of the counter and the source and destination IP addresses and ports. So you take all this information fundamentally, the guy who sent you the stuff, you key hash it. That means that you do a hash of that value together, but you add to the data a secret key. So only if you have the key, you can generate the correct hash. So when you get back, your own sequence number, that at this point you have forgot because you don't care, when you get it, you recompute what you would have created in the few seconds before. And if one of those is actually the sequence number, that's proof that the guy actually received that sequence number from you, and therefore the acknowledgement number is to be accepted as correct. Okay? So we can talk about the details, but the basic thing that you have to understand, fundamentally, you generate your own sequence number. When somebody tries to open a connection to you, you generate your own sequence number, not in a random fashion, but by encoding your IP address, source, and destination port with a key, and you make a hash of it, and you use that as the sequence number. So when you get back your acknowledgement number, like, is this one of mine? And you can go back, and you're the only one who can generate these numbers because it's a keyed hash. That means that it's not just a keyed hash. I mean, there's not just the hash of IP1, IP2, port 1, port 2. It's not just this. There is also a secret value. That means that unless you know this secret value K, you cannot have the right information in that sequence number. And so by doing this, you don't have to keep any memory of the half-open connection. Of course, there are some drawbacks. You have a sequence number that grows faster than normal. Your values are limited to a few. Your maximum segment size value are limited. And also, you cannot use data in your initial SYN packet because, of course, it's, you destroy it. You don't keep track of it. In general, this is a problem with TCP/IP. There are all sorts of state-based attacks. Being TCP a stateful connection communication, you can always, do open a connection and just send 1 packet a minute. If certain operating systems will shut down a connection if they don't see traffic associated to it, but you can always say 1 byte right before they make that decision to keep on, stay there. And so this is a common way to, perform the denial of service attack. Of course, this is worse. I mean, it's not as effective as SYN flooding because you actually have to spend some resources yourself. Because you, on your end, have to also keep a TCP state of some sort to send the right packet, to keep track of the thing. The SYN flooding is cool because you can just send the SYN packets spoofed and you just fill the queue and take down the host. If you want to keep a TCP connection going, you need a lot of hosts. But sometimes, for example, if you have a botnet, you have compromised a lot of hosts, you can open thousands and thousands of connections to one specific, Apache installation and go very, very slow and keep those connections open and eventually exhaust the resources of that single version. And we're going to stop right here.